Howdy. I wanted to be clear about the instructions from class today for your homework problems. Today we considered a problem, we considered a circuit that was subject to a Kirchoff's law analysis. And you remember that to do that, we started by identifying the nodes and currents. And once we had identified the nodes and the currents, then we wrote the Kirchoff's node law, K and L equation, the sum of the currents at A is equal to 0. And then we identified two loops, and we did the sum of voltages around those loops for the Kirchoff's voltage law. And we chose loops 1 and 2 for our analysis, but we noted that loop 3 was possible also. And so that ended up giving us these three equations right here that you remember from class. And then we ended up solving them by elimination. And just to remind you of how that went, we lined up all of our variables here so that the I1s are vertically aligned, the I2s, the I3s are vertically aligned, and the constants are on the other side. And then we chose a variable to eliminate, noting that I1 is a good choice because it appears in only two equations. I2 is also a good choice because it only appears in two equations. I3 is not quite as good a choice, although certainly doable, because it appears in all three equations. And so we chose I1, and we were really happy because I1 requires no multiplication here. We can simply copy our equations straight across. Add them up to get a new equation that has two variables, just like so. And now our elimination has taken three equations with three variables and reduced it to 1, 2 equations in two variables. We can now repeat the process. I have one equation here, and I have one equation here, and if I multiply, renumber these. Here's equation number 1, here's equation number 2. If I multiply equation number 2 by -2, then it will be suitable for eliminating the variable I2. And so that would look like this. I have my first equation, -2I2 plus 2I3 is equal to -5. And my second equation, -I2 minus 3I3 is equal to -5. I'm going to multiply this bottom equation here by -2 to get 2I2 plus 6I3 is equal to +10. And likewise, we have the top equation, which I'm going to leave unchanged, or alternatively, simply multiply by 1, which is invisible. Add up and get 8I3 is equal to 5. 4I3 is equal to 0.63. In this case, it was milliamps because my original resistances were given in kiloohms and the original voltage is given in volts. And having found this, I can now substitute the I3 back into either equation 1 or 2. And we did that in class and found that I2 is equal to 3.2 milliamps. And very quickly thereafter found that I1 was equal to 3.8 milliamps. And all of this is simply a review of what we did in class. So I trust that you're good with it. Then in your homework, I asked you to alternatively solve using the calculator, and so I wanted to remind you of how that goes. When we did a calculator solution, what we were doing was setting up a matrix of coefficients, and the matrix of coefficients comes directly from the right-hand side of this equation, and then we set up a vector of voltages that comes from the other side of the equation. This is the left side, that's the right side. Yep. So my matrix of coefficient comes here from the left side of the equation, and my vector of voltages comes here from the right side of the equation. And we represent this same equation as A times I is equal to V, where A is my matrix of coefficients. In this case, it would be 1, negative 1, negative 1, and negative 1, 0, negative 2, and 0, negative 2, positive 2, times I is equal to 0, negative 5, negative 5. And the idea is that if I can multiply both sides by the inverse matrix A inverse, then that will cancel the A on this side, and I get my matrix, my vector of currents directly as A inverse times V. So if I can set that up on the calculator, then life is very easy. We've done this before, but I wanted to remind you of mechanics. The basic steps that we're going to take are, first of all, set up A as my coefficient matrix, then set up V. In the calculator, we're going to represent this as matrix A. In the calculator, we're going to represent this as matrix B. And we're going to represent it as a 3 by 1 matrix, meaning it has 3 rows and 1 column, which makes it essentially a column vector. Likewise, A is going to be a 3 by 3 matrix. And then once we have that, we're going to calculate A inverse times V. So, just to remind you of how all that goes, we hit matrix, find matrix, there we go. And we're going to edit matrix A and turn that into our coefficient matrix. And we're going to make sure that it has the right dimensions, which are 3 by 3 in this case. And we're going to pull these coefficients here from our problem. You notice I've got a bunch of junk from a previous problem that we did. I'm going to ignore that junk and just enter my coefficients. And let's get those up here so you can see what they look like. Those are negative 1, negative 1, negative 1 across the first row. And so I enter 1, negative 1. Doesn't like that minus sign, so I'm going to have to do that manually. Negative 1 and negative 1. And then I'm going to enter my second row, which was negative 1, 0, negative 2. And then I'm going to enter my third row, which is 0, negative 2, positive 2. If you have your calculator at home, and you should, then follow along and make sure that you're able to do what I've done here. That sets up my coefficient matrix. Now I'm going to set up my voltage vector. So I go back to matrix, and I go back to editing. This time I'm going to edit matrix B. And make sure that it's a column vector with 3 rows and 1 column. And I'll pull those numbers off of the right-hand side of the equation here. 0, negative 5, negative 5. And that looks good. Okay, now that we have all of those set up, that was the detailed part. Now we're ready to do a solution. And so we go to second Well, let's quit out of here entirely. We go to second matrix. And this time, we're going to just pull out the name A so that we can do A inverse and multiply it by the matrix B, which will now compute for us the column of currents. And sure enough, we get 3.75 for I1, 3.1 for I2, and 0.63 for I3. If we compare that to the answers that we have here, it compares very favorably. We're off by 0.1 in I2. Now, having got a solution, whether it is by matrix or whether it is by elimination, we now need to check that solution physically. And to check that solution physically, we put it back into the original circuit. Let's make a copy of that original circuit. Here was our circuit right here. It's really messy. Let's make a copy of that circuit. We're going to have a 10-volt power supply. We're going to have a 1K resistor right here. We're going to have a 5-volt power supply here. And just check the original. Yes, there's a 2K on that end. 2K resistor right here. And then a 2K resistor right there. And what we have discovered through our elimination is that we have current I1 going this way at a value of 3.8 milliamps. And we had an I2 going out this way at a value of 3.2 milliamps. And we had an I3 that ended up going this way. Make sure I got the directions right on that. That seems slightly wrong. I2 is 3.2, I1 is 3.8. Let's make sure that's right. That's right. And in the original circuit, I1, I2, I3. Aha! I had I3 going in the other direction. There it is. We're all better now. So this is 0.63 milliamps, like this. So here's how the checking is going to go. We're going to make sure that the currents add up to 0 and that the voltages add up to 0 as we walk around. And to do that, we need voltage drops across each resistor. A very good way to do that is to figure out voltages at points. Pick a point, call it 0. And it doesn't matter which point, but I like to pick the negative end of a power supply for 0. Then as I go around this loop on the left, this point is going to rise by 10 volts. Then it's going to drop by 1 kilo ohm times 3.8 milliamps. It's going to drop by 3.8 volts. And 10 minus 3.8 gives me 6.2 volts right here at this point. Then as I continue around the loop on the left, I drop by another 5 volts so that I am down to 1.2 volts right here. And then as I go across the 2 kilo ohm resistor, 2 kilo ohms times the current of 0.63 milliamps drops me by 1.26 volts, and that puts me at negative 0.06 volts, which is essentially 0 within rounding error. And so I've come back around my circuit, I've done a loop check here, and my loop checks out. Likewise, when I look at this point, right here at this node, the current going in is 3.8 milliamps, and the current going out is split into 3.2 and 0.63, which adds up to 3.8. So I have a successful current check on that side as well. And then finally, if I take the loop around on the right, I call this point 0 volts, ignoring the rounding error that I got right there. If I call that point 0 volts, and I go around clockwise here, then I'm going to notice that I'm going to be rising to get to 1.26 volts here. Then I'm going to be rising again to get to 6.26 volts here. And then as I come to this point right here, the voltage drop is going to be 2 kiloohms times 3.2 milliamps is 6.4 volts. And that puts me back down to negative 0.2 volts, which is, again, pretty close to 0. It's close enough to say that my math is right. Well, I hope that this is helpful for you, both in terms of seeing how to do calculator solutions and also to check. I know that the process is a painstaking process, and in real life, we don't do all three of these. We do not do elimination and matrix and then go through and do the checking. But in real life, I do usually do a calculator solution followed by checking, or at least spot checking, loops and nodes to make sure that I'm not fooling myself. I will talk to you later.